supply, as it is very hard to find as natural supplies of it are very rare. Okay, for artificial crystals, we have some most prominent examples such as LGS, which is used in some sort of sensors. Biopiezoelectric materials include some very often seen materials such as wood or silk. They have a very good advantage of being very environmentally friendly as they are renewable. They are also lightweight and tough compared to modern ceramics. However, they provide low stability as they deteriorate by the environment. They also have very low piezoelectric properties compared to crystals or ceramics. Lastly is what we will be focusing on the most, piezoelectric ceramics. As mentioned before, there are some lead examples such as PZT that is very often used nowadays. However, we'll be focusing on the lead-free examples as is what we will be making this project on. There are some notable examples such as barium titanate or bismuth ferrite. So now we'll be talking about the parameters that we'll be using for this project, and I'll pass the time over to Mike.
So just now, thank you, Jaden. So just now, Tony also mentioned about B33. So it's called the piezoelectric breaker. So it measures the electrical part generated of high dimension. And for example, in P33, it's in 3D. So it quantifies the effectiveness of a piezoelectric material in converting mechanical energy into electrical energy, or vice versa with stress supply. And the performance indicator is a high P33 value is a more effective piezoelectric material. So just such as the PCT, and very high P33 values, make them excellent candidates for applications requiring strong piezoelectric properties. So another is Curie temperature. So this is the temperature at which a piezoelectric material undergoes a phase transition from ferroelectric state to paraelectric state. So below the Curie temperature is where the material exhibits the piezoelectric properties. When it's above it, it no longer has the piezoelectricity, so it's not good. So it means the higher TC value means a better material for piezoelectrical use. So these are also the comparisons for the piezoelectrical ceramics. So KNN has very high Curie temperature and good piezoelectric properties, but it is very unstable and it may be graded in the harsh environments, which is not good for industrial use. BT has a low Curie point, which is not suitable as well, but it has good piezoelectric properties. EMT has relatively high piezoelectrical properties and good Curie temperature. BFO has a high Curie point, and it's good as it's very stable, but it has average piezoelectrical coefficient. So we would like to improve on these current materials, as we should make a better one to counter all the to improve on the current options. So technologies. So the main technology we use to make a piezoelectrical material is doping modification. So doping basically means introducing small amounts of impurities or substituting ions within a material structure, existing material, to modify its properties. And just changing a little bit can already modify the material by a large amount due to chemical reactions. And by selecting dopants or concentrating concentrations, we can tailor the material properties to achieve the desired piezoelectric performance. So one of the methods to do this is CVD. It is chemical vapor deposition, and it deposits the solid material from gaseous phase. It's a very low contamination risk in making the product, making a material, but it's very high cost, the cost that we cannot bear. So we will use another method that which will be presented, will be mentioned later. So our methodology. So we research on more ceramics, and one of the ceramics we found is BFPT. It's a very high Curie temperature and a good piezoelectric performance. However, there's a very high electrical leakage from the Fe ion inside the BFBT ceramic, which I'll show the equation later. And it will form subsequent it will form secondary phases after the leakage, which makes it very unstable in high temperatures, which is not good. So previous research shows that substituting a lone pair ion Bi3 with a low pair ion of the neodymium, thallium, and ceramium can weaken the lone pair activity to stabilize the BFBT ceramic. So that's where we will be focusing our research on to improve the current BFBT ceramic. So out of the three ion substitutes I mentioned, only the neodymium has not been researched in depth. So the design of ceramium has a very high purity temperature and a good piezoelectrical performance, but the design of thallium also has a good piezoelectrical performance. But we also would like to improve on these characteristics and properties. And neodymium is more harder and more magnetic than the other two options. So we will see how it reacts and how it can improve the BFBT ceramic. So this is our chemical equations. The above is the first design, which is the original BFBT ceramics. So it has a 70% of Bi and Fe and O3, and then with a 0.3%, 30% of PATI3. And we basically doped 0.01 of neodymium inside our second design, which is the doped version, which is the one we'll be focusing on and compare the two results together. This is our design. This is you can see my mouse here, the doped version. This is the original BFBT ceramics. And now we will talk about the material making process. So the material making process, as we already now made our first design, the second design. This is the diagram of the procedure. And this is the picture we took while making the project. We can pass the isoelectric material. Take a look. This the procedure we took making this material. First, we preparation is plating our chemical formula and milling and ciphering. And ciphering is important as we need to find the right molecular size for making this piezoelectric ceramics and then forming a sinter. And then after all this procedure, we need to do testing. And now we will pass to Leo to talk about testing.
Thank you. I will check out some of the testing because our process is very long. Process time is very long and limits you certain types of laboratory. So we would be used to design the testing about the samples in room temperature at HKUSD. This is the D30 meter and the LCR meter. About the D30 meter, this would be testing the piezoelectrical coefficient. That is about how many volts you put into the piezoelectric surrounding chip that can generate how many electricity. And then about the LCR method, this is the common equipment in the laboratory, and we can connect to our test feature to testing the chip capacity and dissipation factor. And about our results, we have two samples. One is the BFBT, and other is the BFBT anti-doping. About the BFBT, our D30 is about 64 pico charge per unit per unit, and the anti-doping one is about 20 pico charge per unit. And about the LCR method result, that show the capacities and the dispersion factors. With the form, we can calculate the electrical consultant that is the ability of the sample to store and release the electrical energy. And that is the result of the two samples. And combine the two samples, this two samples, we can see the non-doping one is better than the anti-doping one. This is strict because in our research, the doping one should be improve the the doping process should be improve the performance of the piezoelectrical surrounding chip. And this is the data from the other research about the DFTP of piezoelectrical construct. And combine the doping one and the non-doping one, we can see our sample is really D33 value is really low. That means maybe some error in our process. About the surrounding factor or impurity contamination or real materials. About the first two problems, we can increase our drying time to remove the water vapor or impurities from the materials. And about the material third problems, materials, we can do other design. Design the other experiment, which is about the different about the freeware deoxys and freeware dioxys. And then put the data into of the model design models and schema.
So for machine learning, as we said, we will be using it to analyze our results. What's important in machine learning is that it can provide us more efficiency, more precision, and also reduce many human errors or some small anomaly data numbers. So what machine learning techniques will we be using? We will be using first secondary modeling, which means it will be creating the environment using our AI model. And this can be done using an algorithm called Gaussian process or polynomial regression. Our second technique will be anomaly detection, which means it will take out small little anomalies in our data and it will filter them out, which will only leave us with some more major and more useful data that we can use. So it can help us significantly improve our efficiency in this project. The third technique we'll be using is predictive modeling, which means, as it states, it can be used to predict the outcome based on several sorts of data sets that we will feed into the model. And it can predict some sort of outcomes without us going through tests, which will reduce our costs because we don't need to actually find material to do the experiment. We can first predict it through the machine learning. And there are some algorithms that we will use, such as linear regression and also support vector machines. We will also use reinforcement learning, which means it will develop a decision-making policy in different environments. For example, it's basically the same as training a little dog, as we will be teaching it that we will give it a reward for every time that it can do something correctly. And we won't give it a reward every time it does something wrong, which is what our algorithm Q-learning is. So what applications will we be using for machine learning? We've been looking through many different possibilities. However, we all have a consensus on COMSOL multiphysics. Why? Because first and foremost, it has a student license and it has free trial. So that means it will reduce our cost of this whole project. At the same time, it is also good at simulating piezoelectric materials experiments because it will utilize what we call multiple physics, which means that it won't just be simulating piezoelectric effects. It will also simulate the area around it, maybe the humidity in a room, maybe it will be the air pressure, maybe it will be different sorts of physics that will be included inside. So it won't just be very single linearly focusing on piezoelectric materials, which will increase the realistic aspect of it. So we also look through other different software such as ANSYS, which requires extensive manual configuration, which means we do not know how to use it properly so that it can unlock its full potential to help us. And MATLAB is similar. It is also very hard to use as we are just mechanical engineering students and we have basically not much programming background. So we won't be able to use MATLAB as well and we can't use it as easily as COMSOL multiphysics, for example. And for simulation, because those two are mostly coding-based, simulation-based, such as TensorFlow or PyTorch, which is a division of MATLAB. And we will also, it is shown to also have struggles in simulating complex physical interactions, which, for example, our experiment piezoelectric materials, piezoelectric effects, also use a very complex physical interaction. So it won't be able to achieve the same results as COMSOL. Okay, so knowing this, what is our future plan? What will we do from this point now on? So first, we will base on the problems and we will redesign the whole control group. And we will also be at the same time using different types of quantity or doping like types of materials, types of formulas maybe, or we will be adjusting the doping quantity, so the percentage that we will use for the dopant. And lastly, we'll be trying to choose a suitable machine learning model because, to be honest, we still have yet to realize how we can use COMSOL to its fullest potential to help us because we're still learning the basics of it for now. And this is our future plan for our orthogonal design model, which will be very detailed here. And also, this will be our working schedule and our so far our progress that is going on. So everything is going pretty good. So this is our citations for all our literature reviews that we've been going through. And that'll be the end of our presentation. So we will open the floor to any questions.
I have a few questions. The first one is for page 42. So what's the difference between three samples? So sample one, sample A, sample B, sample C.
It's the same. Because there possible that we lost the sample or the sample is different in quality, so we make a several sample to test.
Then you need to have a list of source of errors. What are those potential errors in the measurement or in experiments can lead to this kind of different results?
Data error, the possible error. Yeah.
Can you quantify these errors?
When we were doing the experiment, we didn't actually record the room temperature or the humidity, so that might be lost to our experiment. But the empiric contamination and the raw material iron oxide, we suspect it might be because we accidentally or mixed in some Fe3 iron oxide with Fe2 iron oxide, and that may cause some problems with it. And however, because it's already completed, and then we realize the error, we don't have the quantity of the impurity and the error. Yeah,
I see. And also for the machine learning part, are you gonna use all of them? You cover everything about machine learning.
The reason why we are so extensive in this is because to be honest, we don't have that much background in machine learning. So we just basically, these are all not separate things. These are all going to be in the same type. They do not conflict with each other. So, for example, segregated modeling can help predictive modeling because they create more environments, and then so they basically help each other. They complement each other, so they can exist with each other and help each other. It's basically. It comes with the applications. We don't have to actively think of it. It's just more for us to know about the application, how to use it.
I see. Because usually for the machine learning, we have several tasks. The first one is for supervised learning, or regression classification. Second one is for the unsupervised learning, or clustering, what have here also. Third one is for dimension reduction, and the fourth one is for reinforcement learning. So basically, it seems to cover everything. But for each topic, there are tons of algorithms.
Yeah, I agree with you about this comment. So you need to really, although you don't need to start everything, but at least try to identify several possible algorithm which is practical for this particular project. Yeah.
Yes.
Okay.
That's right. So for the simulation part, also for machine learning, you need to collect a lot of data. So those data are from your simulation, right? So your simulation, what is output for your simulation?
The output might be it's to find what we're trying to find. So like the D33, the period temperature.
So it's a distribution.
This
for the 1 point temperature or the distribution of whole temperature.
Realistically, it will be more distribution.
If it's distribution, you should consider a dimension of the temperature. For example, if you have the 100 data points for your temperature output, then your training data should be 1,000 for your machine learning. Because the number of training data should be much larger than the number of dimensions of each data.
So you should care about this one. Be careful. And when you feel machine learning, you should about how much data we need to collect, and what is the computational cost for the simulation as well. You cannot wait forever to get simulation output and collect solid simulation output. You should consider this one as well. Okay, that's all the question.
Okay, I have some question about the goal of this project. Of course, I do have some collaboration with top university, use Berkeley about this kind of how to use piezoelectric material for to design and fabricate this kind of piezoelectric sensor actuator. So from my own this kind of understanding and studies, so that I don't know why you want to start from do research on the material of this piezoelectric material, and then you want to try to develop this kind of AI, this kind of enable this kind of devices. From my point of view, it's a very, very big task. So that most likely it's not suitable for the UG level of this project. If your goal is too, I would say your goal, according to the title, the goal is too ambitious. Huh? Did you say so? Do you have any idea about this kind of? Do you say this? According to your title, I would say probably it can classify as at least master PhD research. If you want to start from the material research and make a device design fabrication, and you also enter with AI, wow, this is very challenging. So why you this kind of I think this no, at least the title is very ambitious. From my point of view, if you try to identify those kind of good pieces of material and then you work on the device, this kind of application and make this kind of prototype, I would say much more practical. Personally, I think it's too challenging for the UG level of the project, unless you are super smart.
Focus on material design.
So your title in that the original
Yes.
is somehow is a change. Oh, now you narrow down the scope now. Oh, okay. So I see. Because I would say in original one is you see design the experiment of a lead-free piezoelectric device for precision manipulation using machine learning.
More than the
Oh, now you change. More than me.
You do have the machine learning.
Yes.
Well, this is my comment.
Nowadays it's a big trend. So we can we have to use it. Otherwise, we are lagging behind. So we will be in some problem in the future. So we have to catch up. So almost every aspect of engineering we can use it.
But my suggestion for your student like here is you need to learn about how to ask a good question or prompt engineering to the AI and use open source AI, this kind of algorithm to help you to do this thing for this particular project engineering. Do that would much practical.
You can
But
go with
prompt engineering, I have way more than 100 AI for chatbot for research, but I just tell you that it will be practical. You try to learn how to do the kind of prompt engineering and how to use the AI, Cloud 3.5, GB4o to write the kind of code for this project. It will be much practical.
AI is very useful. You can talk to the referee.
Yeah. Open source AI on the GitHub.com, and then so that would be much practical. Yeah. But you need to think about turn this kind of mechanical engineering is kind of a project and then very precise kind of question and prompt to the AI help you apply open source AI. You are not computer science. I believe you are not giving your own this kind of algorithm, but how to use those kind of most advanced kind of AI model, which have been now available for everybody like you to use it for this particular engine platform. I mean, that was more important thing. Yeah. Okay. Yeah. Okay, 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 that's it. You can also try to get the this AI tutor for you to learn this kind of thing. There's a one called Reindeer. It's open source Reindeer AI tutor from the one high school student in Australia. You Google and find Reindeer AI tutor, and then let the AI tutor to teach you. Understand? Yeah, okay,
Okay,
okay, okay.
we'll have a meeting, we'll have a meeting. Okay, bye-bye.
Getting open space.
Okay. Meeting.
Attending meeting.
Good morning, professors. Today we present our FIDP progress presentation. Our topic is AI-enabled new generation, low-cost MEMS mirror-based LiDAR in the area of IoT. Our work focuses on developing a compact, low-efficient, scalable LiDAR system with using FPCB MEMS micromirror. These are the four project objectives: conduct parametric design analysis of flexible PCB micromirror, fabricate and experimentally evaluate FPCB micromirror model, then implement FPCB micromirror to work as LiDAR sensor, and finally, integrate FPCB LiDAR sensor with the AI model. This is our FIDP roadmap. In the first 2 to 3 weeks of our semester, we worked on the literature review. Then we worked on the theoretical design from week 4 onwards. At the midway point at week 7, Kavindu worked on the prototype of our flexible PCB. And the last 2 to 3 weeks, when we received our fabricated PCB from a Shenzhen company, we worked on the experimental setup and data collection and analysis. All of us worked on the literature review. Me and Avram worked on the theoretical design and analysis. Kavindu worked on the PCB development because of his prior experience in PCB fabrication. And in the end, all of us worked on the experimental setup, testing, and data collection and analysis. Now I hand over, introduction. LiDAR or light detection and ranging systems use modulated lasers to measure distance and are integrated in application of self-driving cars, AR, VR, robotics, and automation. LiDARs can be classified into two systems, scanning systems and non-scan systems. FPCB micro mirrors reduce cost, aren't as bulky, and leverage electromagnetic induction, actuation, and use Lorentz force by generating alternating current and drive the mirror oscillation. Next one. Now we compare the comparison between our previous FIDP and our current FIDP. The earlier FIDP relied on motorized MEMS scanners and for beam steering, which were bulky and less efficient. Our current FIDP uses FPCB-based MEMS micromirror with electromagnetic actuation for steering. The earlier one also used off-the-shelf parts, which were bulky like the bulky motors and triangular precision. Whereas we use novel design and materials like polyamide. The application focus of the previous one was self-driving cars, whereas we have a broader applicability, including automotive, robotics, AR/VR, and IoT systems. Now I'll hand over to Avram to discuss the progress.
Thanks, Abdul. So before we actually started with the design of the flexible PCB micromirror, we thought it would be prudent to conduct a dimensional analysis to better understand the characteristics of the model. So we used the Buckingham pi formula where the voltage was the input and the angular deflection as the output. And from that, we derived a relationship for the angular deflection as related to the parameters of the PCB model. And from this, we derived a rough optimization guideline, as you can see, in order to maximize the angular deflection, as well as increase the response and the natural frequency of the system. So once we had conducted the dimensional analysis, we moved ahead with the actual design of the PCB prototype. And of course, the first step is to conduct analytical calculations. And in order to do that for our prototype, we divided it into different sections in order to simplify the analytical calculations. So the sections have the same cross-sectional shape and material. And we also made a simplification where the frame was assumed to be stiff, so it was ignored from the calculation. And of course, as a dynamic system, so we considered the 1 degree of freedom MCK model for rotational system, and the analytical calculations were used to find the parameters of this MCK model. So the first parameter we need to find is the moment of inertia, which is fairly straightforward to calculate for rectangular cross sections, especially for beams and series. And using the material properties, we were able to calculate the total moment of inertia for our system. Next, we move on to the torsional stiffness calculation. And for that, first we need to find the torsional constant, which depends on the cross-sectional shape of the beam that you are considering. And from that, we can get the stiffness contribution for each section. And that is summed together depending on the geometry of the model. And what we found is for the total torsional stiffness of our PCB model, a fair estimation would be to take the total torsional stiffness as 2 times the torsional stiffness of the first section, which is actually the 2 beams that are connected to the mirror blade. And we can also see the material properties we use. And it's worth noting that we also consider the variability of the elastic properties of polyamide, and we found the torsional stiffness from there. Next, we move on to the damping coefficient calculation, which is actually an estimation because this is just analytical without experimental values or simulation. But we can be fairly confident with our estimation because we roughly know the quality factor as MEMS micromirror systems tend to be underdamped. And using the previously calculated stiffness and the moment of inertia, we are able to estimate the damping coefficient. And now, once we had done the analytical calculations, we moved ahead with a simulation study. And we used ANSYS to conduct a modal analysis. And you can see the first 4 modes of the frequency analysis in the slide. We tried to use, as you can see, a fine as mesh as possible, and also to, again, account for the aforementioned variabilities in the elastic properties of polyamide. So for our application, for our PCB micromirror, only the mode 1 is relevant for actuation. And as you can see from the results gained from the natural frequency calculation, the error between the analytical solution is within acceptable limits, verifying the solution. And we believe the error is just because of the simplifications we made in the torsional stiffness calculation, because the moment of inertia calculation is actually identical. Yes, so now that we have derived these parameters, we went ahead to the 1DOF MCK model, and we attempted to implement it in MATLAB and to solve the differential equations of the MCK model using MATLAB. However, it is worth noting that we did find a discrepancy between our MCK model using these analytical parameters and the actual experiment. But we do believe that this is just because we had an unreliable estimation of the magnetic field. And this is something Kavandu will speak to more on the PCB design section.
Thank you, everyone. I'll now be going over the two types of PCBs that we have fabricated so far in the project. And first, we have the PCB mirror oscillator, which has so far been the main focus of the project. And we have a Hall effect sensor array to measure the magnetic field strength between the two magnets as well. And overall, when I designed PCBs, I tried to follow these basic design principles that I learned in my prior experience with PCB design. But some of these are not very relevant to our specific design because, for example, our oscillator only has the copper coil and no components, so we didn't have to worry about many of these aspects. So for the oscillator design, I initially tried to design a 4-layer PCB, a 4-layer flexible PCB, which was similar to other designs that were in similar research papers. And some variations that we were considering before designing a first prototype were mainly regarding the torsional beam, namely having a short beam, long beam, or fork beam to see how that affects the characteristics. And we initially proceeded with the fork beam design, and as I mentioned before, it was a 4-layer design. But so we did run into some issues due to the manufacturer that we used. We used JLC PCB, which is one of the more convenient and cheaper options for consumers. And the specific limitations that affected us were the fact that JLC PCB only allows a 2-layer flexible PCB and also a minimum track width and spacing of 0.15 mm, which is much larger than other comparable mirrors. And also it only allows blind through wires and no blind or buried wires. So yeah, we did convert from that previous 4-layer design to a 2-layer design. However, in this design, I did these some additional through wires, which allow the scope for converting this easily to a 4-layer PCB design. And I have those drawings and those designs in the appendix as well. And we also use FR4 stiffener in all areas except for the torsional beam to allow for the easy flexing of the PCB. And yeah, another important thing to note is that we made sure that all adjacent sections of the coil would have the current running in the same direction. So as you can see on the front copper, we have the, from this view at least, we have the current running down on the right side and up on the left side. And likewise for the back copper, we have it down on the right side and up on the left side. And yeah, this is our fabricated oscillator so far. This is yeah, and we'll further go into the experimental setup later on in the presentation. And as for the second prototype that we have been planning to make, that we have actually put into design, we've increased the pin size from 1.27 mm pitch to 2.54, just for the ease of connections. And we've also added holes fastening the PCB onto the experimental setup just to make the entire experiment process much easier and more stable. And for future iteration, we have considered, again, as mentioned before, using different beam geometries, and also perhaps increasing the length, the size of the coil overall, and adding more layers to see how that affects the output frequency and characteristics. Now moving on to the design of the Hall effect sensor array. So we want to experimentally determine the magnetic field strength at different points along the coil. And this was mostly required for the MCK model that Albert was talking about earlier. And we used a linear Hall effect sensor, and as specified by the data sheet, we added the necessary pull-up resistors and bypass capacitors, again, as specified by the data sheet. So our initial design thought process was to try and fit in as many sensors as possible within the area of the FPCB oscillator, just so we can know, at each point along the coil, how much the magnetic field strength was. And because of that, this led to us making a 4-layer design with the components on the back side and all the Hall effect sensors on the front side and all the other components such as the resistors and capacitors on the back side to fit in as many sensors as possible. But that led to the issue that led to us realizing that even though we fit in as many Hall effect sensors as possible, many of these gave us redundant readings due to the fact that they were placed symmetrically. So for example, these two Hall effect sensors would give essentially the same reading due to them being the same distance away from the magnetic field. So this led to us revisiting the design, and this led to us revisiting the design and designing a Hall effect sensor with array with less redundancy. As you can see, all the Hall effect sensors were placed with a 1.25 mm distance apart from each other to make sure that there were no redundancy in the readings. And this also had the benefit of having components on one side only, which reduced the cost as well. And yeah, we did, however, run into some issues during the testing with some inconsistent zero values when there was no magnet present. And there are some factors that this could be down to, and we'll be hoping to improve this in future iterations. And as for improvements, again, we want to increase the size of the pins from 1.27 mm pitch to 2.54 just to make sure we can just, directly use jumper cables for the ease of attaching instead of having to solder everything. And we also plan to review the Arduino code that we use to read the Hall effect sense measurements to ensure that there are no errors there. Thank you. And Arvid will go over the experimental setup.
Okay, so this is the physical model we developed using SolidWorks and 3D printing using PLA filament. So as you can see, this is the setup that securely holds our FPCB and also holds the two magnets, which are N52 magnets of the size 3 centimeter by 1 centimeter by half centimeter. In this experimental setup, you can see that how our fabricated FPCB is securely placed on our holder with two N52 magnets equidistantly placed on either sides. The scan angle response of the FPCB mirror was characterized by various frequencies and voltages. In this experimental setup, you can see that we have a measurement board with a graph paper attached, which is placed at a distance known to us A from the setup or from the FPCB setup. There are sinusoidal voltage generated from the function generator, which are passed to the FPCB setup. When a laser OM128658 shines on our FPCB, the deflection trajectory is showcased on the measurement board on the graph paper, and the length of the trajectory is W. We can use the trigonometric function to calculate the total angular displacement. Alpha is equal to 2 tan inverse W by 2 by T. As you can see in this experiment video, FPCB responses are response as an input frequency from the function generated is varied. There is a significant increase as the angular deflection reaches resonance frequency. Now I'll pass on to Arvind to discuss some of the experimental results.
Thank you. So now let's discuss the results of the experiment. We actually conducted two experiments. One was a frequency response characterization, which is conducted at a constant 8 volts. And from that, we observed the resonant frequency to be at 51 hertz, which is actually right in the middle of our prediction from the simulation model when you account for the variability and elastic properties of polyimide. And next, we had a voltage response characterization, which was conducted at the frequency, the resonant frequency that we found. And from this, we can observe the linear angular response with voltage with a peak of 28 degrees at 9 volts. And now with this experimental data and the natural frequency, we can derive the damping ratio from the bandwidth, and also with the natural frequency and damping ratio, we can develop an empirical normalized 1 degree of freedom MCK model. And that is done with the equations given here and also implemented from the charts that we found using MATLAB and of course, the experimental data itself. So from this empirical parameters, we can use it with the frequency response function in order to compare the analytical model with the experimental data. And the equations used in MATLAB are shown here, and the charts that we derived from the MATLAB code are presented here. And you can see from the MATLAB code that we actually have R squared fit for the frequency response function of 0.802, which I think shows a fairly close fit between the experimental data and theoretical model. But of course, there is scope for improvement. We believe if we take more readings close to the natural frequency, we should get a better fit. And from this, we are also able to observe the voltage sensitivity of our PCB at 2.47 degrees per volt. And this is like a summary of the results that we have, and comparing it with one of the prominent papers we found in literature that also works on flexible PCBs. And it is worth noting that our natural frequency and angular displacement is significantly less than theirs. However, another point that's worth noting, we only use 2-layer PCB due to the aforementioned manufacturer limitations, whereas they use 4. Furthermore, there is a huge scope for improvement in our case with the parametric design optimization, as this is just the first prototype that we have developed. I'll pass it over to Kyle.
Thank you, Arvind. So now that we've gone over what we have done so far in the semester, I'll just go over quickly some of the learnings that we have gained and some work that is left to do in the future. So regarding the software side, I did have some prior experience using Yi-Kuen to design PCBs, but it did help me, but going over PCB design for this semester has helped me brush up on some of those skills. And Avram and Arvid did use ANSYS and MATLAB for the 1DOF MCK model and also the model analysis as we talked about previously. Regarding the experimental setups, we did learn how to use Hall effect sensors to measure the magnetic field strength. However, as mentioned before, there were some issues, so that is again something that we can work on in the future. And another important thing that we noted was to make sure to thoroughly go through all experimental procedures beforehand, before actually going to the lab to conduct the experiments. Because there are a few times that we had planned to conduct an experiment, but when we tried to actually start to do the experiment, we realized that there were adjustments or changes that had to be made to the setup, or to the prototype, or to the magnet holder, which delayed our entire experiment process. And another important thing to note is that we learned is how real-world character factors can affect our experiments in a way that we wouldn't initially anticipate. For example, something as small as a graph paper having a fold in some section would make the reading of the displacement different. And yeah, now talk about some future work that we have left to do going forward. So we intend to conduct parametric study using the improved 1DOF MCK models to optimize our design once we actually finalize the design of our Hall effect sensor array and improve the readings from that. And we also plan to implement this FPCB mirror in as a LiDAR sensor as well in the future. And we do intend to redesign the magnet holder for better customization of the magnet distance from the FPCB to improve some characteristics as desired, and also to improve the reflectivity of the FPCB for more reliable laser reading. And finally, we have purchased an Arduino integrated AI module as recommended by a professor, and we intend to use this to improve the capabilities of our FPCB mirror once we actually integrate it with the LiDAR system. And yeah, thank you very much. That's at the end of our presentation so far, and we'll be happy to take information.
Question. Okay, the project is done with theoretical. So lots of work. But I have a question about which non what is your desired system?
Yeah, I can do it.
But you final system. Yeah.
So, as for this semester, our aim was sort of to use this paper as a reference to gauge our progress. So, it would be our aim, at least for next semester, to improve our characteristics to have an even superior angular displacement to the previous papers. That being said, it remains to be seen how.
Want to be better than these references.
That would be ideal, but it remains to be seen how we implement that. And also, we also, apart from just the design of the PCB, we also hope to implement it as a sensor. So that is another consideration for next semester.
Okay, I also have a question. When you try to present your prediction of your the kind of response from your one feeder model, you said there's some error, right? Compared with experiment result. So did you really carefully think about what's the key reason you have this kind of problem?
Yeah.
Especially I've noticed that if you're using JLC PCB to make your this kind of prototype, actually it's a multi-layer structure with not only one material. So that the substrate most likely they have a P4 and also polyimide. So you in your model or your calculation, you only assume one material or one layer. So do you say, I just want to know that you have to be careful, try to say, oh, what's the reason? What's the reason you have this kind of your simulation result is not has some not consistent with external result? Do you know that JLC PCB have multi-layer? They have not only somehow you say polyimide. If you look carefully, it's not only polyimide. That's a multi-layer structure. It's a copper. Things do that.
Oh yeah. In the design and for the 1DOF
MCK.
We actually mostly considered only the movement of the torsional beam. And
Okay.
the torsional beam, I think you can see if I can just quickly.
So for torsion beam, is it only use polyimide?
Yeah, it is only the polyimide, and there is that there on these two sections of the torsional beam, we have the small section of the copper trace, which I think we didn't account for because we thought it was a bit it would be negligible to account for that. And there is FR4 stiffener on all these edges, so we assume those to be rigid. But for this current prototype, I only added a 0.1 mm FR4 stiffener. But in the future, we decided to add a thicker FR4 stiffener just to make sure the rigid assumption is more reasonable.
To add to Kaundu's point, the torsional beams themselves, we do know are only polyimide. And after speaking with actually one of the postgrad students that are helping us with the project, he did mention that for the torsional stiffness calculation, it is almost entirely the contribution from the beam. The plate itself is not supposed to flex. So it is, we believe it could be a reasonable estimation. And the main error for our MCK model is because we were not able to accurately find the magnetic field, which is something we need to work on with the Hall flexors.
Just notice you have been focusing your work on oscillator sensor. So are these the new designs? That means the references, they do not use oscillator, they do not use Hall sensor. They also use different oscillator or different sensor.
Yeah, I think there are similar papers that use an oscillator, but some of them do use quite expensive methods of fabrication, and they use a lot of layers, which is not really accessible for a consumer to do. For example, I checked this exact design of the oscillator, and I checked multiple different PCB fabrication houses that allow for multi-layer flexible PCBs, and it increased the cost from. So I believe that prototype was a 2-layer PCB from JLC, which cost us around $30 US. And the cheapest alternative that I could find that used a 4-layer flex PCB was actually closer to $200 US. So we think that our niche or our differentiation is the low cost. Yes.
But yes, you're right.
Your simpler design was the
Actually,
worst performance.
so actually, I think this is also quite critical. You need to address the issue. Why? When you look at your,
if you can put in a comparison,
what?
I mean, it's not an exact comparison because you can actually see it's almost half. We use half
less.
the
Yeah.
Furthermore, the thickness of the trace space that we use is much higher than what they use.
No, but your design is simplified.
But then because of the manufacturing limitation.
That's a problem.
Yes, but the reason for that is the only reason it's simplified is because of manufacturer constraints. We intended to make it a 4-layer superior model, but that's something we learned as we were prototyping. It's important to take into consideration the constraints.
It's better to compare your design with the reference, because this is a design.
Yes.
It's not cut down of others' design.
Yeah.
If you cut down others' design, the same design, and then even performance is worse. So that's not good. So you need to propose a new design, the performance similar, but your cost cheaper, better, and that's a better design.
I think what Bertrand also mentioned very important thing. Now you have choices. In the sense that there's so many different ways to fabricate PCB. You have faster PCB and JLC PCB, Howling PCB, and also HDI PCB. So I think now you should think about carefully to compare. Once you have your own way to build the kind of a model, you compare different kind of a fabrication process, and then and show what a family of different design in terms of performance and cost. Right? I think now you both sides you can do this kind of thing. Both carefully design optimization, not only performance but even the cost.
If I can bring up another point,
right?
It's actually just our first prototype.
Yeah, but I would say it would be important for you to think out different kind of technology.
Another differentiating factor that we are considering is the actual design of the beams.
Yeah,
it will still be electromagnetically actuated, but with the ferrometric design optimization, we do hope to differentiate ourselves from the previous papers. This is just our first prototype that was, to have a solid reference.
Another comment is you may want to learn from Professor Lin and use Berkeley's work. They're using AI to optimize the mechanical design for this kind of MEMS devices. You say so. There's you can look at Professor Lin, my collaborator, use Berkeley, how using AI to optimize this kind of MCK. That's another level thing you think about.
AI is
Huh?
free from new design.
I think there's
New
room.
design is old design.
Yeah, this is the old design, but actually, you look at I actually sent you to look at my collaborator at UC They you try to use it to come with
Yeah.
even fancy design to optimize the kind of involved response. Okay, anyway, I'll say I understand there's always room for you to make better. Yeah, yeah.
I think we did.
I think
You
yeah.
mentioned AI in terms of future work. I guess using AI in terms of designing the actual oscillator is not something that we consider, but yeah, we'll definitely try to include that in
yeah.
our design choices.
Yeah. Using AI to help you on design. Also, even the prototype, both are okay.
I
Yeah.
think at the moment, our
Yeah.
focus was to use AI on optimizing the sensor readings. I think this is helpful feedback.
Yeah, yeah. Okay, I think I probably I think we run out of time. Maybe go to the next one. Yeah. Okay, then. Sure. I also use AI to make a summary of a thing. Then you should think about how to AI. Oh, okay. AI will help you to think about how to give you some this kind of feedback for your following work.
Thank you.
Okay.
Nice day.
Okay. Okay.
Okay.
resolution. I'm responsible for object detection. Peter is responsible for video restoration, and Ben is responsible for image 2D to 3D reconstruction. So this is our timeline of the project. So in the first 3 weeks, we did some background research and initial planning. And during the weeks 4 to 9, we did algorithm research and testing. So for weeks 10 to 16, which is still ongoing right now, we will do model development for separate parts. So let's move on to project progress.
Thank you, Lincoln. So the first main function of our camera is image conversion and decompression. Our main target for this image conversion and decompression is we would like it to be expressible as a string as shown in the figure, and it can compress to reduce larger than 90% of the file size. And when it is compression, it can recover 100% of the file size. And this can be very flexible between compression and decompression. And also, both of them can applicable for different file types such as JPEG, PNG, bitmap, and etc. And also for video as well. We require have an efficient process also. So our first approach is a non-AI method. We can compress the image by reduce the image size and by reduce the image quality and also changing the file type. The advantage of this method is it can successfully reduce 90% of the file size, and it has a fast process time. However, when the original image is original JPEG, this can only reduce 20% of the original of the file size. Also, it cannot do the decompression in this non-AI method algorithm. So we move on to the second approach, which is we use the dictionary learning. The dictionary learning allows us to transform 2D vector into 1D vector, and by changing the parameter as shown as the PowerPoint, like we can change the batch size, the number of atoms, and etc. We can have a different output called image quality. And there are some, this is original image, and this is compressed with and transformed into a grayscale. And there's some reconstructed example of the image. So as you can see, the image the reconstructed image is acceptable. However, sometimes as this method is not a lossless method. Sometimes it will have some loosey pixel and they will produce some black box. So we are going to fix it with maybe some smoothing image technique. And yeah, so after talking about the compression and decompression, we are going to talk about another important function of our camera, which is image resolution. So basically, we would like to make a very low resolution image to become a very high resolution image. So our target, of course, is increase the image resolution, and also which is acceptable for both image and video. And also, we would like it to have an efficient process time also. So our first approach is using the GAN, which is generative adversary network. This method can quadruple the dimension of the original image and also 60 times the number of pixels of the original image. So as you can see here, we input a very low resolution image here. After the generator, we can have an output which is have a high resolution image. However, before the input and output, we have used many images inside a data set and data sets to train the generator and train the module. So here we use 7,000 images for the training, and you can see the result here. The top hand for each image, the top two images is some old method. Like the left one is the bicubic method. The right one is the Westland method. Our GA method is the left bottom one, and the right bottom one is the original image. So as you can see, the GA method has the best quality for super resolution, and the PSNR number is also 30 point something, which is very good. However, when the image is lack of the detail in color, we cannot reconstruct it
to a very detailed image. However, but you can see the PSNL number is also around 30, which means we successfully increase the resolution, but we cannot reproduce the detailed data. So this is some problem we are facing and we are going to solve later. And now let me pass to Peter to talk about the video restoration. So thank you, Alan. Why we need restoration? The reason is that sometimes the camera is under poor conditions. The recorded video may become blurry, or it's too dark to see, or it's too noisy. And these are the types of distortion we focus on. And because they're quite different, so different types of models, AI models are required. For denoising, I've choose this fast DVD net, and because it is a very fast model, and the network show here the denoising blocks here give some CNN layers, and the video, the input video will be split into different frames, and in each iterations, the model will use the neighboring frames to do the denoising, and this can make the video output be more coherent. And here I add some noise to the original video and pass it to the denoising model. And I have used the PSNR, which measure the image quality, and the SSIM measure the structural similarity compared to the original video. And the higher the value means the better the result. And you can see the output video indeed have higher values for both measures. And also by comparing these regions, you can see the noisy background above is removed in the video. And the advantage is that it takes 0.15 seconds to denoise an image, and it is very fast. And because of the use of this very computational efficient CNN layers. And here we have a graph to compare what has among the similar models, and you can see how the model takes less time, way less time than other models. And for deburring, I choose the Western. It is a transformer-based model that uses CNN for better performance. And the network is like this. It contains many transformer blocks, and in each block, there's two modules. And they both use the CNN for to capture the spatial features. And also it contains some skip connections here. This can allow the model to skip some minor layers. And also it can increase the efficiency. And I have some input output samples here. You can see the words and numbers are more clear now compared to the input after the development. And also for the two pages, we can see an improvement as well. And for the time result, it takes 3.19 seconds to deburr an image. And it's fast because of the use of skip connection and the CNN. And also by comparing with the other models on the number of flops. The flops here means the number of floating operation per second. And you can see the Westerner is on the right side, which take left side, which take less flops during processing. And so here we'll give a short future plan of my part. I will work more on the line enhancement part. And currently, I think we will pass the video frame to free restoration models sequentially. But in the future, I will analyze whether it is feasible to have just one single and powerful model to do all the restoration part. Now I would like to pass on the time to Lincoln to talk about the object detection.
Thanks. Object detection is a technique that uses neural networks to localize and classify objects in image. It has a wide range of applications, from medical imaging to self-driving cars. In this project, we aim to apply object detection techniques for monitoring 3D printing processes. During our initial exploration of object detection algorithms, we encountered several options such as RCNN and YOLO. We examined the background, operational mechanisms, advantages, and drawbacks of each algorithm. Notably, RCNN and YOLO seem to be used more frequently compared to others. Following a discussion with Professor Liu, we were advised to concentrate on more recent AI and big data related algorithms. Professor Liu highlighted machine learning and deep learning frameworks like GAN and LLM. Additionally, Professor Liu suggested exploring algorithms capable of estimating target object distances from the camera using angles or reference objects. Subsequently, incorporating Professor Liu's insights, we went searching for object detection algorithms. aligning closely with our project's objectives. 3 algorithms, namely AI object detection, object avoidance and detection for blind people, later referred as OAD, and YOLO multi-camera object detection and distance estimation, later referred as multi-camera algorithm, have shown potential as strong contenders. Here are some pictures taken during testing for AI object detection. It shows the algorithm's ability to recognize objects like people and bottles within the same frame. However, there are limitations like misclassifying objects. As you can see here, mistaking an iPad and a sheet of paper for a book, which is likely due to a limited dataset with a few object categories. The algorithm lacks distance detection, exhibit fluctuations with multiple objects in a frame, and display overall inaccuracy. Therefore, we did not choose this algorithm for our project. For OAD, it includes functions like voice recognition, object detection, and distance detection. For object detection, it can identify objects like chairs, hats, and pens. For distance detection, it detects the exact distance between the camera and the object. When this distance falls below a set threshold, it initiates a beeping alert. To use it in our project, we must modify the program to display distance information without generating the beeping sound. However, since this algorithm is not designed specifically for object detection, we continue searching for other algorithms that is more suitable for our project. For multi-camera algorithm, stereoscopy-based measurements was used to measure the distance of the object. Here's a figure that shows the parameters that will be used during the calculation. This method would be computationally complex, but it can be resolved by the implementation of AI. The greatest challenge in this method is to calibrate the cameras. As you can see in the figure, this method requires 2 cameras. So precise placement of cameras to reduce error is essential for accurate results. The implementation of the algorithm is as follows. 2 video streams are processed independently by YOLO. After that, the stereoscopy-based measurements method will be applied for distance estimation. We have yet to test out the algorithm, but we are expecting to see something like this. As you can see, the object identified and the distance is shown above the object. In evaluation of this algorithm, it uses stereoscopy-based measurements, YOLO neural networks, and it can provide functions of object detection and distance detection. Challenges such as dual camera setup and calibration exist, yet these could create opportunities for potential improvements in 3D reconstruction. It is also worth to note that this algorithm does not work well for long distances and small objects, but we could simply overcome this by adjusting the camera's proximity. Among the algorithms considered, this choice aligns most closely with our project objectives. Now I'll pass the time back to talk about 2D to 3D reconstruction.
Thank you, Lincoln. So imagine transforming a single input image into a detailed 3D model. With our AI-enhanced surveillance camera, 3D reconstructions become a reality. The functionality allows manufacturers to visualize their operations in new ways, monitor equipment, analyze workflows, and identify issues with precisions like cloth nozzles and undesirable printed shape. Particularly for additive manufacturing, which is 3D printing, it also allows us for remote monitoring. From enhanced monitoring to smarter decision making, 3D reconstructions open up endless possibilities. So to achieve the functionality, my first approach is the depth anything feed tool. This algorithm turns the single input image into a depth map. So the left-hand side I can see is actually the depth map generated by the depth anything feed tool algorithms. And the right-hand side is actually the 3D reconstructed model based on the depth map itself. And you can see that the disadvantage is very clear. 3D reconstructions is actually not well constructed because there's something wrong with the 3D constructed algorithm and need to be improved. But for the depth anything feed tool algorithms, it's actually showing quite good for the relative depth of the object. And advantage is that it only use a mono camera, which means it doesn't need 2 cameras for depth estimation. So to fix the reconstruction model, the second approach is the point cloud reconstructions. So the left-hand side you can see is an input image and it's feed to the depth anything feed tool again. But this time I changed the reconstruction model to point cloud. So this time you can see that the car is actually here and here. And the disadvantage is that for depth anything feed tool algorithms, you need to hard code the distance between the camera and the object, which means every single time you change the camera position, you have to change the algorithm's parameters based on the distance. If the distance is
the input distance is like shorter, it will be more compressed. If it's like in a larger integer, and it's going to be lengthened. So the final approach adopted to address this problem is the algorithm called the instant mesh. So the odd column is actually a single input image, and the even columns are the 3D reconstructed model based on the generative AI algorithms called the instant mesh. You can see that it achieves a better accuracy, and it also the advantage is that it doesn't need two cameras for depth estimation, because it's like completely based on the generative AI, and you only need a single input image to fit into the model to construct 3D reconstructions. So how does it work? It's actually two separate models. The first model is turning a single input image to the multi-field, and from a multi-field to the final reconstructed models. And it's actually two separated models. And you can see here is the performance of our instant mesh algorithms. Plus to bottom is actually the performance. And you can see that it's like performed relatively better than the other compare other mainstream AI reconstruction algorithms. So now let me pass the time to Peter and Ellen to talk about our future plan.
So at this moment, our works and our projects may seem like there are four different projects for four different cameras. Therefore, we are going to integrate them all together to become a real AI enhanced camera. So that we can have compression and decompression for saving the storage space, and also super resolution for more accurate identification for object detection and 2D to 3D, or also denoising. So also we are going to buy an AI enhanced camera from Raspberry Pi, which is quite useful for our project and after our research. Therefore, and also Peter will talk about the potential approach.
One concern is that video-related algorithms are really computationally demanding, and process of our camera may not be powerful enough to do all the tasks remaining. So we are considering to shift some of the computational load to the cloud or to our PC. And you may think, how is going to transfer a video to the cloud or PC? Then we are thinking to use some wireless approach, like we may use some Wi-Fi or Bluetooth, or some XP wireless module from the Arduino. And that's all we want to test out in the future. And this is the end of our presentation. We are open up for the Q&A session.
That's overall interacting does. This is a design project, but it looks like you are doing separation of it. So what is your final design system?
So our final design is actually having all these algorithms integrated to AI cameras. So you will be having a camera with all the AI algorithms.
Just put everything together. What is your final solution? What are the reference points? What are your systems? You want to achieve them. So these are not available. Maybe you have to video every part. Very. So what about who activate that? What about phones compared to the existing systems?
Because the existing solutions that there is like lack of the market of like AI integrated camera. Camera can only be camera, and you have to feed it to some software for some identification. And we hope that our AI camera can actually deal with all the algorithms like object detections, 3D reconstructions with our integrated algorithms.
Example, you say you want to have a super resolution. So for it to find the solution, you can if there is an object, can you make a micrometer or even and you can go this kind of resolution?
For at this moment, our everyone can only just
your resolution is about pixel resolution.
yeah, pixel resolution.
So you are saying that you are going to make the detected object
Yeah, the approach.
So the object got a size. So how the size will be detected? You got you got measure every millimeter, every micrometer, or every
For this function, I think it's not only depends on the algorithm, but also depends on the original camera, the state.
So then you need to show your systems. So what kind of system you want to develop?
We are now working on this system design. We are integrate all algorithm together and make it become a build camera and test.
So looks like your project is still in the stage of literature review. You find many different algorithms. You have a try, this algorithm is good, this algorithm is good. What about overall design? Design audits design. You need to show what's new in what design.
Yeah, I think currently we are working on
Understanding of others.
and also
understanding different algorithms.
yeah. And in the later stage,
You need to do this kind of understanding.
okay.
Need to, that means other teams not only understand what's going on, but also they try something. They have overall objectives. What is the way? But European is still in the state of understanding what others doing. Different team algorithm, different very algorithm. You can kind of something. So you're doing the comparison, understanding. So this is still in the state of review. So it's not fast enough. You need to live by what is it? So this is in the situation. So get faster.
We will take the times of winter semester.
So also what are your timeline?
Yeah.
So the gantry chart. So you need to show your.
This is the time.
It's too not detailed. The gantry chart is not. It's too simple. So you need to do some progress. Not fast. Or detail. Okay, the work. Control of time. Thank you.
I also have some general comment because from my point of view, I do have some PhD student work for the industry. For example, I have a PhD work for Apple and Huawei, and also even Intel, and also OVI. OVI is the biggest this kind of a small image sensor company in the world. So the one of top three. So that did you look at those kind of existing product, this kind of a small image sensor or camera integrate with this AI function? Is that you are engineer? You need to think about little review what is being done in the published paper and also the real product. So that, but from my recommendation is most likely I would hope you can think about how to use existing the kind of device component you buy and then just focus on a real application about the kind of you post the various camera for solve some real world problem in the our major, right? It's MAE, mechanical engineering or something for specific, for example, surveillance or some of maybe safety of some building engineering or something. One specific application which apply this kind of AI camera for some of the real problem in our mechanical engineering, building engineering, or aerospace engineering, I would say would be better. Most likely, I don't believe you can really come with this kind of very deep kind of work in these kind of algorithm and also this kind of integration to doing that. But how to identify those specific kind of important problem from your the kind of major, right? For that would be, and then turn into this kind of prototype, show it you can solve some problem. Yeah.
Maybe like with them.
Did you try to look at the existing product? At least I do know several company make this kind of thing. All this kind of new smartphone has AI enabled, like iPhone 10 beyond have NPU and also thing and this kind of OVI that and also Sony they really do a 3D IC this kind of integration, make a single image sensor with this kind of processor and even AI module. So that you need to get existing product on the market and they think about how you compare, right? Now you really compare even little review, even product, and then to see okay, what's new, how can you contribute from this kind of using this kind of FYDP project in this kind of specific area. Yeah.
So find a reference products, reference system, show your system and do a comparison. You understand?
For example, you can see this is a new iPhone 16 I just bought. So they have this kind of function. Yeah. They have AI, generate AI chip. In the integrate with the TSMC 3nm technology and camera thing, they can do all these things. But this is not only one. iPhone too expensive, but there's some edge computing, the thing you can think about to buy from Alibaba across border in Shenzhen. That's more than one company make this kind of thing with camera, with this AI across border in Shenzhen, like M5 Stack. Look at the company you can buy M5 Stack, and there's at least two companies, SiP, they are making this kind of AIoT module with camera, and the cost is around about $200 or $300 only. But of course, the performance is not as good as the iPhone 16, but there's some unique application, I would say. Okay.
A few comments just for
Yeah.
So three questions. First, you need to differentiate what's your difference between product and other product. Not only the algorithm level, but also product level. And you can improve just one specific thing, or improve cost, or improve function, or improve accuracy. Because here you didn't, again, I mentioned before, you didn't list all the metric you want to compare with others' work. You only have a TSLR for one single image, but it's not enough for metric as well. And another one is you need to focus on one application. Because is mechanical engineering, so we focus more on the manufacturing process and where you manufacture. So one application, of course, you know here is for 3D printing, right? You want to monitor 3D printing, but you didn't mention here for 3D printing. So this is for 3D printing, you may have different challenges compared to other commercial cameras. But how can we use your camera to address this specific problem? That is more important. You can think about it for later.
Okay.
Okay.
Thank you. Thank you.
Thank you.
Yes.
Here, not to use Google. You can use Google Stack. So just log in with your Google username.
Okay, so 20 minutes.
Good morning, professors. Our topic title is AI-enabled virtual representation for 3D bioprinting of disease model. I am Maria Hermione. This is Jasmine. This is Matthew, and this is Audrey. So, our project aims to create a bioprinter. So I'm sure most of you have heard of bioprinting, which utilizes additive manufacturing to create living tissues and organs. It uses specific bioink, which is a mixture of hydrogel and living cells. So bioprinting has great potential in the medical field, but it has not been popularized yet. Why? Well, there are several reasons. For example, it's quite expensive, both the machine and the material. Also, it's relatively slow because it needs a lot of time to print and to test the materials. And lastly, most of the printers on the market are closed source, which greatly hinders the possibility for research. So therefore, we sense there's a need for a more cost-effective and scalable solution. That's why we want to design a bioprinter based on the FDM printer in the market. So our printer would be able to print several materials at the same time. So for our case, would be 2 types of hydrogel and a PLA or any other sort of filaments. So it would also be able to perform real-time failure detection and allow the user to adjust the print setting on the fly. So ultimately, we'd like to be able to predict failures with reconstructed 3D models of our prints, and also train a model to automatically respond to the error detected. So this way, we could greatly reduce the waste of materials and the time due to their prints. And also, since we are reconstructing 3D models for simulation and also failure detection, we could guarantee the precision and also its functionality. And last but not least, because we're using mostly open source materials for our project, it would be easily reproduced. So how would our bioprinting work? But first, we'll start with a simulation to ensure that the design geometry would be functional. And then we'll send the design to print. And during the print, we would perform failure detection and also dynamic correction. And this cycle will do until the print is finished. After the print is finished, we will construct a 3D model of it and perform simulation again to ensure that despite the imperfection during the prints, that our geometry still works.
So here are some details for the prediction process. We will first capture images from 4 different angles of our 3D print. These images will then go through some image processing, such as removing the background or centering the print to the center. And we will go through diagnosis and prognosis in parallel. For diagnosis, we will build machine learning models to detect any error present in the current print. And for prognosis, we will first reconstruct a 3D model from the 2D images. And after we have reconstructed the model, we will go through some simulation and analysis. And combining the results of diagnosis and prognosis, the printer will make decision making to decide whether it should continue, terminate, or calibrate the chip.
So we have divided our project into several aspects as shown as follows. As for our timeline, we have started defining our project scopes and reviewing the documents in September. And in October, we've started working on the printer and the algorithm. In November, we've worked on supplementing what we've done in October and also fine-tuning the results. So by the end of this year, we expect to be able to detect failures during the print and also perform AI-initiated termination.
Great. Good morning, I'm Matthew. So I'm in charge of the hardware of the printer. So let's take a look at a 3D printer. We are using a Creality Ender-free 3D printer. This is a very cheap, very easily found 3D printer on the market. So because of our bioprinter, we have incorporated 2 multi-material nozzles, as well as retain the original PLA nozzle over here. Our print bed, well, we have limited our print volume to 100 meters and 100 meters times 150 meters tall. And let's take a look at the multi-material prints. So here we have 2 syringes, and we can replace them with different kinds of materials. On your left side, you will see it's more like a gel-like substance. On the right, it's more like a cream substance. So this allows for us to have multi-materials and to have multi-color prints. The syringes are controlled by stepper motors, and it is going to be attached to the nozzle over here. So we can take a look. This will be the nozzle that prints the multi-material prints. Because bio-ink is relatively expensive, we can use aloe vera or moisturizing cream, some cheaper cosmetics as a replacement to collect our training data. So as you can see, we have designed this fixture for our and as well as this original PLA nozzle, so we can combine them during our prints. So because one of our key part of our FYDP is reconstruction, so we have incorporated 4 cameras into our 3D printer to capture and do a 3D reconstruction. So they will be placed on the side and on the top of the print in a 3D pyramid fashion here. So here are some concept pictures of how the reconstructed or the photos will look like. So on the side, we have the side view over here and the top view over here. So we are planning to capture photos every 5 to 10 layers, or else the print may not be thick enough for it to be reconstructed. So here are some common errors we found on our 3D printer, with most notably intrusion and over extrusion. So under extrusion is when the layer starts to thin, there's not enough material coming out of the nozzle, and it may lead to instability of the print cannot stick together, and it will fall apart. Over extrusion is when there's too much material coming out of the printer, and the print nozzle may actually slide past the nozzle and causing very bumpy surfaces. So here you have an over extrusion piece. We also are planning to target spaghetti failure. So when the nozzle, when the filament cannot stick to the print anymore, and they just start printing a bit there. So that is spaghetti failure. So we will plan to terminate the print if we encounter such failure. The last one is stringing. So stringing is there are these tiny little strings that stick to the print surfaces. These are very minor imperfections and can be adjusted via changing the print parameters, the print speed, the printing temperature, and the retraction settings also.
Okay, so let's move on to the software part. I'll be doing the print error detection. So here's an overview of what we have done in Python. We will build a machine learning model to detect whether our current print has error, and if so, we will classify the type of errors. So right now for PLA, we have defined 10 class categories. So just worth to note that some errors cannot be fixed by calibrating G-code, which means we must fix it by hand. So if we detected such kind of error, we will simply terminate the 3D printing. And for other errors such as under or over extrusion, these can be fixed by automatic recalibration. So for our model, we have chosen we will use convolutional neural network for CNN. So why we chose CNN is because they are good for dealing with images, and its convolutional filters can learn and extract the features of print errors. And also it's a deep learning network where it's captured the error patterns well. I've tried transfer learning with fine-tuning the hyperparameters with several popular pre-trained CNN models, including VGG 16 and 19, GoogleNet, and various RedNets. So basically our detection process will look like this. We will have 4 images from 4 different angles. Each of them will be put into a CNN network. And also we have an additional parameter of the type of material. So you can see it will be either hydrogen or PLA. And the printer will go through the detection process and decide whether it has error or not. So for the data set, we will have separate data set for PLA and hydrogel. And because we have yet to set up cameras on our printer, so we can only collect a small amount of training data from our file printers or from capturing images from our mobile phones. So I've looked into some online data sets, but still there is quite limited data sets on bioprinting and 3D printing that has similar class categories as our projects, and moreover, there's no 3D printing data sets for hydrogen. And so I've looked into a data set from Kaggle. It has over 16,000 images of PLA prints, and this data set has 4 categories, whether there's no problem, under extrusion, stringing, or spaghetti. So here are some examples of the images from the dataset. And I wanted to first investigate the performance of different pre-trained models. So I've extracted an 800 image subset with each class having 200 images. So for our CNN training, these are the results on the 800 image subset. And the input dimensions for the image are 224 by 224 by 3. And here are the hyperparameters that I've used. So from the results, we can observe that GoogleNet and ResNet has much better performance on the test set compared to VGG. And we can observe that VGG, the training time for VGG that's even on GPU is significantly longer time than the other networks. And the test accuracy isn't really good as well. So we decided to start fine-tuning the hyperparameters on VGG. So here are the results. Here are some learning curve and accuracy curves for the various networks. So I've also tried some hyperparameters for ResNet 18. I've tried these for different learning rates, and the performance of the validation set is the best for learning rate 0.401 with around 90% validation. And I've also tried different optimizers, including Atom, SGD with momentum, parameter prop, and Adagraph. So it's observed that Atom and the Adagraph has the best validation accuracy for ResNet. So I've also tried to input some of some image of prints that is from Howler picture, and there's still a long way to do to train and to experiment with our model. But these are our results. So for the 3 instructions, here's the part 1 for the answers. So we're going to collect the images from multiple angles, as each side of the 3D print is important for us. And we'll be using the Raspberry Pi 4, which originally has only one camera slot. So we have an extended around the sequence 4 cameras attached to the Raspberry Pi. And after collecting the images, we'll be importing into the training model with Pillow, which is a Python library. We'll be also doing pre-processing on every possible. Now we're going to do depth estimation. So essentially, PyTorch will be using its built-in model to estimate the distance between a camera and each point on the silhouette of the 3D printed object. So as you can see, the darker parts are nearer, where the model thinks the camera is nearer to the object, and the lighter part is a part where it thinks it's further. So it's not quite accurate. As you can see, behind is just a wall with the same distance from the camera, but from objects either together. So we have to we'll have to research on better models and better accuracies. So next time we're gonna generate the points out from the depth image. So it's gonna have a lot of vectors on every point on the image. And finally, we're doing as we have 4 images and 4 point clouds, we have to combine them together to generate a 3D model. So we'll be using the iterative closed point algorithm. So it works by finding the distances between each point on the point cloud, and through each iteration, it's gonna minimize the distance between the points and to get an optimal the shortest distance between all the point clouds and obtain a combined mesh point. And finally, we'll be using the OpenThread library to generate from the merge point cloud.
Thank you, Jensen. Now with the 3D reconstructed model on hand, we can work on the simulation. So we have identified a need for 2 separate simulations, which would be the geometry simulation and the functional simulation. For the geometry part, we would be concerning with the failures during the printing process. As for the functional simulation, we'll be focusing on the performance during the usage. So, as we mentioned, we will be more concerned on the failures during the printing process for the geometry simulation. So we will be using the 3D model reconstructed every 10 to 30 layers, depending on the printing speed and also the complexity of the geometry. And we'll identify the failures and defects due to gravity and the consistency with those models. And with this data on hand, we would like to train an AI model to predict the failure printing errors from the initial layers. So for this simulation, we will be using SolidWorks because it's relatively fast and it could simulate imperfect geometries. So here's an example for our test. So as you can see, we have created a 3D model imperfect vessel with Blender with these parameters. And you can see that on the wall, it's quite rough and it has a sharp inclination. So for the material, we have customized a hydrogel with the status, which is the average of the hydrogel in the market, because we don't have a specific data set for our own hydrogel yet. Okay. So these would be the results. So we have fixed a face on the bottom to mimic structure standing on the printing plate, and this is how it reacts to gravity. So this would be total deformation, and the next one would be strain. So now let's move on to functional simulation. As we've mentioned, functional simulation concerns the failures after the print. So during the functional environment. So we would be performing this when the print is finished, because we will be using the whole geometry for the simulation. So we would like to see how the imperfection would affect its performance, and also see that what kind of imperfection would be acceptable. With this data, we would also like to predict how imperfections we would like to use this data to train an AI model for prediction as well. So we would be using a two-way side-by-side simulation for the functional simulation, which would be a fluid structural interaction simulation, because we need to see how the printed geometry, which is solid, would react to the fluid interaction, which would be pulsed in our situation. So for our choice of application, we would be using ANSYS because it's relatively accurate and it allows us to customize the material and also the velocity profile of the fluid. In our case, we'll be customizing hydrogel and also blood, and we would need a specific velocity profile to mimic the blood. However, ANSYS could not compute model with significant imperfection and its closed source, so there would be a little sacrifice on the accuracy. So we have reconstructed a model as shown on that corner with these parameters. So for the materials, we would be using ANSYS rubber, which is an elastic material, because as we mentioned, we don't have the data for the hydrogel yet. As for the fluid, we are customizing a blood with these following status. Okay. So for we have also designed a velocity profile as shown to mimic the blood. So this is our simulation setting. The yellow part would be the concerned geometry, and for the orange and the green part would be there to mimic the attachment to other blood vessels and also allow free movement of our geometry. And these would be the results. The silhouette part is the original position, and the colored part would be how the structure reacts.
Right. So for future works, we're currently mid stage, and we're going to create a solution for adjusting the nozzle height of the different the nozzle height during the print, so the nozzle don't stick to the print. We're also going to manually introduce imperfections during the print by changing the flow rate, the speed, the temperature, so that we can better train our AI model. Lastly, we're going to fine tune our camera setup so it can better capture the pictures for the 3D reconstruction.
So for the software part, we will work on some data processing techniques such as background removal or data augmentation. We will also continue fine-tuning the hyperparameters for the CNN model to make it more robust. For the reconstruction, we consider particular methods that can reconstruct the fine details of every part of the 3D printer.
Maybe the end. Thank you.
Oh, this part is not big. Must be very challenging problem. But bioprinter must be very attractive. Because the people buy or live thousands. So must be attractive. However, our project is a piece. So people will want to find out what you are design. But one thing noticed that so if Rita so you are doing the design and bioprinter, to finally your work something related to prediction, 3D reconstruction, simulation, information. These are not bioprinters. So how this work on the
So if we go back, this entire 3D printer, it's a commercialized 3D printer that originally does not have all of these kind of fixtures, the yellow part, the syringes, they're originally not here. So we took a commercialized 3D printer and modified it such that we can print biomaterials in the future. So
okay. So you have a design, then what is agent? These other visuals by if you add something, you need to scale up things. Just add their function. Just start. People still find new things, but they work. You make up something. That means this printer is not. You add some part. Then your printer performance, how they are compared with some other things. You need to really check. This part would be this.
So
you really deliver a design that is and comparable for the back and the existing. Or what about existing?
So over here, I believe that Professor Liu's group has an actual bioprinter, a commercialized but by cell
existing. You're going to use this one to add things new. So what is the final delivery? What about specification? Specification versus performance.
So what I'm hearing is the comparison between a commercialized bioprinter by a company versus our own designed printer.
Yeah, just wondering how many are available in the market. So not just the professor.
Yeah.
I mean, if you just based on Professor Liu's it's good. Okay, reference. But we also compare with the companies. So how many companies are making bioprinters? How many laboratories are making
Yes, in terms of bioprinters, I believe that it is a experiment carried out by all over the world from a big company. So yeah, that would probably be in our Twitter reports. Twitter report because
you haven't finished the kind of at least one page or one summary to compare, right? Existing work, right? What have been done in the public paper or even some commercial products 3D print. I believe there must have some company making this thing, but somehow, yeah, somehow you didn't have some simple comparison, right, about existing work.
Another one you need to show what's new. Not only you deliver a design, also need to show what's new. So it's not this kind of solving some simple minor problems. You can look at it.
The new design being like the
So that means you review the existing design all over, then deliver something new that are not available out of this is design. Design must be cannot be something. So when you deliver something not existing and do a comparison with the rest of then that is it. So this part really is simple. Another one is about presentation. You did all this, you didn't show objective fact. So why do you want to do 3D reconstruction? Why do you want to do simulation? So also, why there are deformation if you go to build 44? We're very totally confused. This is 3D printer, but how you get deformation? Where's the force? How the force are high?
Oh, this is forces gravity.
Gravity.
Because we are printing hydrogel, which is not rigid, so therefore it will deform under gravity. And also because this film express small is about 1 millimeter.
Is this a problem? I also recognize that this how serious is serious? This is serious. But if this problem is minor, then not. You understand? You need first justify the work.
You define some of quantitative key performance, right? Measure for your this kind of your project, engineering project and goal, right? And then if the deformation requirement is maybe 1 centimeter, 1 millimeter, 1 micron, or 1 millimeter, then if there's no very clear, they show this thing, and then actually it's meaningless to see if deformation is going it has a problem or not problem. That somehow your presentation also not clear. Engineer.
Can we do something justify what is correct? That is just help you to imagine. If we don't simulate the deformation, the final work will not work. And they say, oh, it's doing right. And also you show, oh, these are the people who are doing this one, and we do this one. So we need to do all this work together. Not suddenly show, oh, there is a deformation. Where's it?
You can either do it in the experiments or push literature review.
Yeah, to see the deform. Yeah, that's fast.
Another sense, but you need to do this work. Why do we need to do this work? Other people doing the same one, people will get lost. Maybe very necessary, but we don't know. So I think we sure. Right? Not only in today's project, maybe in your future one. Whatever you do, you show first why would you do it. That's a native. So these are the first steps. Of course, you show the hard work of simulation. AI training, GPU.
So
all these add together for what? Or get lost. Get lost.
That's why at the very beginning I mentioned the important thing here is a virtual model. Why you need a virtual model? You need a virtual model to interact with experiments. Then you need this whole system, but you didn't explain this as well.
Another one is your time control. You didn't show your country.
Your project. Oh,
projects.
yeah.
Management is also a job of engineer. Your lack of time control, even you do excellent work for student. So you need to show how many work, what's there. Don't work, but very emphasize on something, but the other artificial.
All this group project, I understand. So it's you have a your individual contribution from each member of this FID team, but maybe project leader need to think about how to put that together, or let your team member to think about how each individual can put together as the whole, as a group project. Somehow, yeah, there's also lack of this kind of integration from the team leader. Yeah. Okay. Yeah.
Yeah, for first page, okay, just give a big picture. What these different sessions can be grouped together. Yeah.
So the bioprinter is very useful.
Important, but it's difficult. As political is in general, I'm pretty sure it's an important topic for sure. Yeah.
So, for example, our department, one professor passed away, only 79. He 90 years old.
If you can make this kind of organ, replace no failure of the organ, make an organ and replacement, everybody can live up to 100 years old. It's a important test, but it's not easy. It's not easy. It's not easy. Yeah. 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 Okay.